For 24 years, 9 months, and 13 days, human beings have lived continuously in space. Not visited, not passed through, lived. Around 400 kilometers above your head, right now as you watch this, there are people eating dinner, doing science, and sleeping in a tin cylinder held together by welds, bolts, and a geopolitical agreement that is quietly falling apart. The International Space Station is the most expensive object ever built by human hands, $150 billion, the product of 15 nations, thousands of engineers, and 5 space agencies who once pointed missiles at each other and decided, against all odds, to build something extraordinary together instead. Every week, somewhere on the internet, there is a video showing astronauts floating gracefully, conducting experiments, waving at cameras during spacewalks. The PR machine is extraordinarily good, and much of what it shows is real. But here is what almost nobody is talking about. The station has been losing air for 5 years, not slowly, faster every year. And as of August 2024, NASA classified that leak at a 5 by 5, the highest possible risk score on their entire safety scale. 2 space agencies cannot agree on whether it could catastrophically fail. They cannot even agree on what catastrophic means. The first medical emergency in the station's 25-year history happened in January 2026, forcing a crew to cut short their mission. Up to 70% of astronauts who spend long durations on board develop a syndrome that permanently damages their eyesight. And in 2030, if everything goes according to plan, which, as you are about to see, it almost certainly will not, a 450-ton structure the size of a football field will fall from the sky, and the question of who controls that fall depends entirely on Russia, a country that has not committed to the station beyond 2028, a country that is currently at war. Tonight, we are going to look at what is actually happening to the International Space Station, not the press release version, not the highlight reel, the real version. The one that lives in NASA's Office of the Inspector General reports and the Aerospace Safety Advisory Panel assessments and the academic journals that nobody reads at the press conferences. If that is the kind of story you want to fall asleep knowing someone is telling honestly, get comfortable. This one builds slowly, and where it ends up is somewhere I genuinely did not expect when I started researching it. Let's get into it. Part 1. What the ISS actually is, and why it matters. Before we go anywhere uncomfortable, I want to spend real time on what the International Space Station genuinely represents, because the story I'm about to tell you only lands with full force if you first understand the magnitude of what humanity actually built up there. The ISS began assembly in 1998. The first crew, NASA astronaut Bill Shepard and Russian cosmonauts Yuri Gudzenko and Sergei Krikalev, arrived on November 2, 2000, and have not left it unoccupied since. That is 25 years of continuous human presence in orbit, a quarter of a century. No weather events, no budget fights, no geopolitical crises, no global pandemic has broken that chain of habitation. Every single day for 25 years, someone has woken up in space, looked out a window 400 kilometers above the surface of the Earth, and gone to work. That is not a small thing, and the numbers that define the station are almost too large to hold in your head. The ISS is 109 meters long. That is longer than a football field, including the end zones. It weighs approximately 420,000 kilograms, or roughly 925,000 pounds. It has an internal pressurized volume of 915 cubic meters, about the interior space of a 6-bedroom house. It has 2 bathrooms, a gymnasium, 6 sleeping quarters, and a 360-degree observation cupola with windows facing the Earth that astronauts call one of the most awe-inspiring views a human being can experience. It orbits at an altitude of between 400 and 420 kilometers, traveling at approximately 7.66 kilometers per second, completing one full orbit of the Earth every 90 minutes. This means that everyone living aboard the station experiences 16 sunrises and 16 sunsets every single day. Think about that for a moment. 16 sunrises. 16 times a day, the Earth's limb glows orange and then gold and then white as the sun crests the horizon, and the astronauts on board have become so accustomed to it that most of them say they barely notice it anymore. The construction of the station required 42 assembly flights over more than a decade. Astronauts and cosmonauts have conducted more than 270 spacewalks to build, maintain, and upgrade it, spending a cumulative total of over 1,700 hours working outside in the vacuum of space. The solar arrays that power the station span 73 meters from tip to tip, generating up to 120 kilowatts of electricity, enough to power more than 40 average American homes. More than 270 people from 20 countries have lived aboard it. They have conducted over 4,000 separate scientific experiments, producing more than 4,400 published research papers that have advanced our understanding of everything from bone density to combustion to the behavior of fluids in microgravity. Medicines developed partially through ISS research are now in clinical use on Earth. Material science breakthroughs made possible by the unique properties of microgravity have found their way into industrial manufacturing. Cancer research conducted in the absence of gravity has revealed things about tumor biology that ground-based labs simply could not have found. In 2015, NASA astronaut Scott Kelly returned from a one-year mission on the ISS, during which his identical twin brother, Mark Kelly, remained on Earth. The Kelly twins study, as it became known, was one of the most extraordinary experiments in the history of human biology. Scientists compared the two brothers across dozens of metrics: gene expression, microbiome composition, cognitive performance, telomere length, cardiovascular function, before, during, and after Scott's year in space. What they found reshaped how we think about the human body in microgravity. And crucially, it revealed things that nobody could have predicted before the experiment was run. The station has survived solar storms. It has survived geopolitical crises that briefly threatened its operation, including the aftermath of the Challenger disaster and the Columbia tragedy. It survived the 2003 period when NASA was grounded and the station briefly ran on a crew of just 2 people, the minimum needed to keep it alive. It has survived, so far, a debris field that is growing more dangerous every year. There is a cupola on the Earth-facing side of the station, installed in 2010, that is made of 7 windows arranged in a dome. Astronauts call it the window on the world. It is where they go to photograph thunderstorms from above, to watch the aurora borealis curl and ripple across the magnetic poles, to see the lights of cities glittering against the black of continents at night. Multiple astronauts have described looking out of that window and being unable to speak. NASA flight surgeon Dr. Natasha Chow has noted that the psychological effect of seeing the full arc of the Earth from orbit, what researchers call the overview effect, is one of the most consistently reported transformative experiences among crew members. The overview effect, a term coined by author Frank White in 1987, is the cognitive shift in awareness that astronauts report upon seeing the Earth from space. It is described uniformly as a sudden, visceral understanding of the planet's fragility, its unity, and the arbitrary nature of the borders that divide it. Astronauts who have experienced it describe a before and after, a line between who they were before they saw the Earth from 400 kilometers up and who they became afterward. The station is the reason that experience has been available to more than 270 people from 20 nations, rather than just the dozen or so who went to the moon. And then there is the simple fact of what the ISS represents politically. It was conceived during the Cold War's final years as a bridge between the American and Soviet space programs that had been adversaries for 30 years. It was built during the turbulent 1990s when Russia was economically devastated and its space program was barely surviving. American money kept Russian engineers employed. Russian engineering expertise helped keep the station functional during periods when NASA's capacity was constrained. It has continued to operate as a joint venture through the annexation of Crimea in 2014, through sanctions and diplomatic crises, and the severing of almost every other space relationship between the West and Moscow. That is what the ISS is: an extraordinary machine, a platform for extraordinary science, a symbol of what human beings are capable of when they decide that the thing they want to build is more important than the things that divide them. I want you to hold all of that in your mind as we go forward, because the story I'm about to tell you is not a story about failure. The ISS is not a failure, but the data underneath the celebration is telling a story that the press conferences have not told you. And the gap between the two is wider than it has ever been, narrowing toward a hard deadline in 2030 and operating exactly the kind of institutional dynamics that we know from documented historical experience tend to produce catastrophic outcomes when they are left unaddressed. Here is the part that almost nobody is talking about. Part 2: The station that is losing air. I want to start with a number. 3.7 pounds per day. That is how much atmosphere the International Space Station was losing as of April 2024. Not a catastrophic number in isolation, not an emergency by any narrow definition of the word, but a number with a history behind it that, once you understand it, changes how you think about everything that comes after. To understand the leak, you need to understand a small piece of ISS geography. The station is divided into two primary segments: the American orbital segment, which contains the modules built and operated by NASA and its partners in Canada, Europe, and Japan, and the Russian orbital segment, which contains the modules built and operated by Roscosmos. The leak is in the Russian segment. Specifically, it is in a component called the PRK, the Service Module Transfer Tunnel. This is a connecting passage between the Zvezda module, which serves as the living quarters for Russian cosmonauts, and a docking port used by Soyuz and Progress spacecraft. It is essentially a hallway, a pressurized tube that allows crew members to move between parts of the station and that provides a docking port for the spacecraft that bring them supplies and, if necessary, carry them home. The leak was first detected in 2019, a small, slow seep of air, barely measurable above baseline. Engineers noted it. It was documented. And because the station continued to function normally, because no one was in danger, because the leak rate was low, it was classified as a manageable problem and placed in the queue of things that needed monitoring. That is not negligence. That is normal engineering practice. You cannot stop operations every time a number changes by a small amount. You monitor it, you track it, you wait for more data. The problem is what the data showed over the next 5 years. In 2022, NASA began making regular reports about the leak to its Aerospace Safety Advisory Panel. By then, the leak rate had been growing slowly and consistently for 3 years. Still not an emergency, still not, by any definition, an immediate threat to the crew. In February 2024, ISS Program Manager Joel Montalbano told reporters that the leak rate had increased to 2.4 pounds of atmosphere per day. That was a significant jump from the historic low of 0.2 pounds per day measured earlier in the station's history. He described it as not an impact right now on crew safety or vehicle operations, but something for everybody to be aware of. 6 weeks later, the leak rate jumped again. By April 2024, it had reached 3.7 pounds per day, a 50% increase in roughly 2 months. NASA's Internal Inspector General report for September 2024 described what happened next. the ISS program elevated the Service Module Transfer Tunnel leak risk to the highest level in its risk management system. In NASA's formal risk scoring framework, risks are rated on a 5x5 scale. 5 likelihood, meaning the event is expected to occur. 5 consequence, meaning the outcome would be catastrophic. As of August 2024, the PRK leak was scored as a 5x5. Let me be precise about what that means, because it is easy to let the bureaucratic language obscure the reality. A 5x5 risk score does not mean an accident is imminent. It means that if the failure mode occurs, the outcome would be catastrophic, and that the probability of that failure mode occurring is not negligible. It means the risk has been assessed by the people whose job it is to assess risk, and they have placed it in the highest possible category. NASA's own Inspector General report stated it plainly. Cracks and air leaks in the tunnel are a top safety risk. Now, here is what makes the leak especially troubling. After 5 years of investigation, neither NASA nor Roscosmos knows with certainty what is causing it. The engineers have narrowed their focus to the welds, both internal and external, in the PRK module. They believe the cracks that are allowing air to escape originated at or near these welds. But the root cause of the crack initiation has not been identified, and the two agencies don't agree on what that root cause is. Russian engineers believe the cracks are the result of high cyclic fatigue from micro vibrations. The station generates constant small vibrations from its mechanical systems, flywheel energy storage pumps, thermal management pumps, docking events, thruster firings. The Russian hypothesis is that these vibrations, accumulating over decades, have stressed the PRK's walls at their weakest points, the welds, to the point of cracking. It is a credible hypothesis. High cycle fatigue is a well-documented failure mode in aerospace structures. NASA's hypothesis is more complicated. The agency believes the cracks are multi-causal, involving not just mechanical vibrations, but also pressure fluctuations, residual stresses from the original manufacturing of the module, material property variations in the specific alloys used in the PRK, and decades of thermal cycling. Every 90 minutes, as the station passes from sunlight into shadow and back again, its external structure swings through a temperature range of roughly 280 degrees Celsius. Sunlit surfaces can reach plus 120 degrees. Shadowed surfaces drop to minus 160 degrees. Multiply that thermal swing by 90 minutes, by 16 orbits per day, by 365 days per year, by 26 years, and you begin to understand the cumulative mechanical stress that is invisible until it is not. The two agencies have not reached agreement, and the consequences of that disagreement are not merely academic. As Bob Cabana, a former NASA astronaut who now chairs the ISS Advisory Committee, told a public hearing in November 2024, the two teams do not have a common understanding of what the likely root cause is or the severity of the consequences of these leaks. Then he said something that deserves its own paragraph. The Russians believe continued operations are safe, but they can't prove it to our satisfaction. And the US believes that it is not safe, but we can't prove it to the Russian satisfaction. Read that sentence again. Two space agencies, jointly operating a crewed station with 6 people aboard, at the highest risk score on NASA's scale, cannot prove to each other whether or not the situation is safe. Roscosmos believes a catastrophic disintegration of the PRK is not realistic. They believe they can monitor the leak, seal the hatch to the tunnel when it is not in use, and manage the situation through to the station's deorbit in 2030. They are confident. NASA has described the possibility of catastrophic failure as a live concern. They are not confident. The interim solution has been to seal the hatch to the PRK module whenever it is not actively in use. This reduces air loss by limiting exposure time, but it does not address the underlying structural problem. The cracks are still there. They are still growing. The leak rate, which was 0.2 pounds per day in the early years, reached 3.7 pounds per day in April 2024. If the hatch must be permanently sealed, not temporarily, but permanently, the station loses one of its 4 Russian docking ports. That port is currently used for Soyuz crew spacecraft and Progress ships. Losing it would significantly constrain how the Russian segment can be accessed and supplied. It would complicate crew rotation logistics, and it would represent an admission that a structural problem on the station has reached a point beyond the ability of the operators to reverse. There is one more detail that I want to sit with for a moment, because I think it captures the texture of this situation in a way that the leak rate numbers cannot. Investigators have had difficulty even locating all the cracks. The suspected crack sites are, according to NASA's statement to CNN, very small, not visible with the naked eye, and they are located in areas with brackets and pipelines that make it physically difficult to get diagnostic tools into position. Engineers have been locating some of the leaks using floating tea leaves, releasing particles into the air and watching where the air current carries them. The most advanced human-built structure in history, $150 billion, 15 nations, 25 years of continuous occupation, and engineers are using tea leaves to find the cracks. That is not a metaphor. That is the documented reality. Part 3. What the station is doing to the people inside it. The station is losing air, and the people it is holding are quietly accumulating damage in ways that will not be fully visible for years or decades. I want to begin with the most recent and dramatic data point, because it happened in January 2026, and it was the first of its kind in the station's entire history. NASA astronaut Mike Fink was eating dinner on January 7, 2026, aboard the International Space Station. He was a member of the SpaceX Crew 11 mission, which had launched in August 2025 and was scheduled for a standard 6-month rotation. Fink, 59, is one of NASA's most experienced astronauts. He has logged more cumulative time in space than almost any other American. And then, without warning, he could not speak. For approximately 20 minutes, Fink lost the ability to form words. His crewmates gathered around him with concern. He felt no pain. He had no prior symptoms. The episode passed, and when it ended, he felt completely normal. But the flight surgeons on the ground were not taking any chances. After evaluation, the decision was made to cut the mission short. The Crew 11 mission was terminated early, and in January 2026, Fink and his crew returned to Earth. In the space station's 25-year history, it was the first time a medical problem in orbit had forced a mission to be cut short. Fink later described the episode as likely a space-related thing. The exact cause has not been publicly confirmed, but the timing, on a man who had spent more cumulative time in space than almost any other living person, raises a question that is very hard to look away from. What is long-duration spaceflight doing to the human brain? The honest answer is, we know some things, we suspect more things, and we are genuinely uncertain about a great deal. Here is what we know with confidence. When a human being lives in microgravity, the fluid dynamics of the body change in ways that evolution did not design for. On Earth, gravity pulls bodily fluids toward your feet. Your cardiovascular system has spent millions of years of evolutionary development learning to push blood upward toward the brain and heart against that constant downward pull. Remove the pull, and something unexpected happens. The fluid shifts upward toward the head, constantly. The result is a suite of changes that affects virtually every astronaut who spends significant time in space, but that becomes more severe with longer durations. Astronauts describe a permanent sensation of mild head congestion, like having a cold that never goes away. Their faces swell slightly. Their legs thin out as the fluid that normally pools in the lower limbs redistributes toward the torso and head. But the most serious consequence is what that upward fluid pressure does to the eyes and the brain. The condition is called Spaceflight-Associated Neuroocular Syndrome, or SANS. It was formally described and named relatively recently. The acronym was coined around 2016, though the symptoms had been observed for years before anyone understood what was causing them. The syndrome involves a constellation of structural changes to the eye driven by elevated intracranial pressure, swelling of the optic nerve disc, folds in the retina, flattening of the back of the eyeball, and narrowing of the venous drainage pathways that normally carry fluid away from the brain. These changes cause measurable vision impairment. Some astronauts have returned from long missions needing stronger glasses prescriptions than when they left. Some have reported blurry vision during the mission that improved after returning to Earth. And in some cases, according to NASA's own published data, the changes may be permanent. Up to 70% of astronauts who spend long periods aboard the ISS show signs of SANS. 70%. This is not a rare complication. It is the near universal biological response to the specific fluid environment created by long-duration weightlessness. The implications for future deep space exploration are severe. A 6-month mission to the ISS involves roughly 6 months of upward fluid pressure against the optic nerve. A mission to Mars, the closest Mars approaches Earth, would take approximately 6 to 7 months just to get there, with a 500-day stay on the surface and another 6 to 7 months to return. That is a total potential exposure of nearly 2 years, with no ability to return to Earth if vision degradation reaches the point of incapacitation. We are currently operating a 25-year-old laboratory in which 70% of long-duration residents develop a syndrome that can permanently damage their vision. And the leading edge of that research, the data we need to understand whether the damage is reversible, at what threshold it becomes permanent, and whether any countermeasure can prevent it, is being generated slowly by the very people living on board. University of Florida researcher Dr. Rachel Seidler, one of the leading experts on spaceflight-associated neurological changes, has noted that astronauts' brains exhibit measurable structural compensation after returning to Earth. The brain recruits additional neural pathways to return to pre-flight performance levels. But the recovery of brain function is gradual. The functional compensation that shows up in brain imaging scans is typically not resolved until 6 months after landing, and for some astronauts, structural changes observed in MRI scans persist beyond that window. Bone density is another layer of the problem. In microgravity, bones that are normally weight-bearing, the spine, the hips, the legs, are no longer bearing weight. The cellular mechanisms that maintain bone density on Earth depend on mechanical loading. Remove the load, and the body begins to quietly disassemble its own skeleton. Without a rigorous daily exercise regimen, the current ISS protocol requires 2.5 hours of structured exercise per day, split between cardiovascular and resistance training. Astronauts can lose 1 to 2% of bone density per month if they do not exercise rigorously every single day of their mission. Muscle atrophy happens on a similar timescale. Without gravity to work against, muscle mass degrades rapidly. Skin thins and becomes fragile. The immune system changes. Early research published in scientific reports found that the microbial communities in astronauts' gastrointestinal tract, skin, and airways all shifted measurably during ISS missions in ways associated with alterations in immune function. Skin rashes and hypersensitivity episodes are common enough aboard the station that they appear as a documented pattern in the microbiome research. And then there is radiation. The ISS orbits within the Earth's magnetosphere, which provides substantial shielding from the deepest radiation of interplanetary space. This is one of the crucial differences between a mission to the ISS and a mission to the Moon or Mars. The magnetosphere provides a protective bubble that the station lives inside. But within the magnetosphere doesn't mean radiation-free. According to reporting from Al Jazeera, astronauts on missions lasting 6 months or longer receive more than 10 times the radiation naturally occurring on Earth. The ISS was not placed in its orbit arbitrarily. It was chosen in part because it is below the most intense bands of radiation, but it is still a radiation environment that exceeds what any human body evolved to handle. The cumulative cancer risk for long-duration ISS residents is measurable and has been a subject of ongoing NASA research for 2 decades. About 7% of astronauts' active genes showed disrupted expression after long missions, and while most of these return to baseline after returning to Earth, a small percentage do not. Let me bring all of these threads together for a moment, because individually they sound manageable. Bone density loss, managed with exercise. Muscle atrophy, managed with resistance training. Radiation exposure, managed with shielding and mission length limits. SANS, monitored, partially managed, not fully understood, and present in 70% of cases. But these are not independent problems being solved one at a time. They are simultaneous, compounding, ongoing stressors on human bodies that are spending months in an environment that evolution did not prepare for. Every day on the ISS, the human beings inside it are accumulating biological debt. Some of it is repaid when they return to Earth. Some of it is repaid slowly over months of rehabilitation. And some of it, the fraction that the researchers concern most, is debt that does not appear to be fully repaid at all. The first medical evacuation in the history of the International Space Station happened in January 2026, in a program that has operated continuously for 25 years with hundreds of residents. That is a remarkable safety record. But it is also a data point that sits against a background of accumulating biological evidence suggesting that the effects of long-duration spaceflight are more serious and less reversible than the public narrative implies. Suni Williams and Butch Wilmore spent 9 months on the ISS in 2024 and early 2025, not by choice, but because the Boeing Starliner capsule that was supposed to carry them home had a thruster malfunction and was judged too risky to fly with crew on board. 9 months. They were supposed to be there for 8 days. When they returned to Earth in March 2025, they could not walk unassisted. Their cardiovascular systems, their balance systems, their muscular systems had all adapted to weightlessness and required time and rehabilitation to readapt to gravity. This is Part 4. The Cloud. There is a threat to the International Space Station that has no engineering solution, no workaround, and no negotiated agreement that mitigates it. It is not internal to the station. It is not in the crew. It is outside, surrounding the station on every orbit, and it is getting worse every year. As of early 2026, the European Space Agency's Space Environment Statistics tracked more than 40,000 artificial objects in orbit above the Earth. These are the objects large enough to catalog: chunks of defunct satellites, spent rocket stages, fragments from deliberate anti-satellite weapons tests, shards from historic in-orbit collisions. The population of objects too small to track individually but large enough to be lethal runs, by current estimates, to approximately 130 million pieces of orbital debris at 1 centimeter or larger. At orbital velocities, a 1 centimeter fragment of aluminum carries the kinetic energy of a hand grenade. A 10 centimeter fragment hits with the energy of a large explosive charge. And the ISS, at 109 meters long with an enormous cross-sectional area, is the largest and slowest maneuvering crewed object in low Earth orbit. The station has performed more than 40 debris avoidance maneuvers since it became operational in 1999. These are orbital burns, firings of thrusters on docked Progress cargo craft, designed to raise or lower the station's orbit enough to increase the margin between its path and a tracked piece of debris. The most recent significant one occurred on April 30th, 2025, when the ISS fired its Progress 91 thrusters for 3 minutes and 33 seconds to avoid a fragment from a Chinese Long March rocket launched in 2005. NASA calculated that without the maneuver, the fragment would have passed within 0.4 miles of the station. But here is the part that the 40 maneuver statistic does not capture. Those maneuvers only protect against tracked debris, objects that can be cataloged, objects large enough for ground-based radar to see. The estimated 500,000 objects between 1 and 10 centimeters, the ones that are large enough to cause a catastrophic hull breach but too small to track individually, are invisible to the station's operators. There is no radar system that can locate them, no trajectory analysis that can predict where they will be, and no maneuver that can be pre-planned to avoid them. The station's protection against these objects is entirely passive. The Whipple shielding installed on the crew modules, which consists of layers of aluminum and Kevlar composite material designed to detonate small impactors before they reach the pressure hull. The Whipple shields are real protection. They are hit frequently. Small impacts are routine, and the ISS has accumulated what researchers estimate to be the equivalent of 200 to 400 years of satellite operational exposure to debris. It has not been destroyed. It has not come close to being destroyed. But has not been destroyed is not the same as is safe, and the mathematics of the debris environment are changing in a direction that should concern anyone paying attention. In 2007, China conducted a deliberate anti-satellite missile test, destroying its own Fengyun 1C weather satellite at approximately 850 kilometers altitude. The debris field was significant enough that the ISS crew was ordered to shelter in their docked Soyuz spacecraft as a precaution. The test was widely condemned by the international space community. Russia has not committed to a moratorium on such tests. The ESA's 2025 Space Environment Report reached a conclusion that deserves to be stated clearly. Even if humanity launched no new objects into orbit today and never launched again, the current debris population is dense enough in certain orbital regimes that it will continue to grow. Debris fragments collide with each other, generating more fragments, which collide with more objects, generating more fragments still. This cascading process, described by NASA scientist Donald Kessler in a 1978 paper and now known as the Kessler syndrome, has no known active reversal mechanism. Active debris removal missions are being developed. ESA's Clear Space 1 mission is one of several efforts to begin physically removing the most dangerous cataloged objects from orbit. But these missions are in early development, face extraordinary technical challenges, and operate in a legal and political environment where removing someone else's satellite, even a defunct one, requires permissions and agreements that do not currently exist at scale. The window from June 2024, which had to be inspected before a scheduled astronaut return, was found to have been impacted by microscopic debris, material too small to be tracked but large enough to compromise the seal. The return was delayed and a different vehicle substituted. As space debris expert Moriba Jha described it, our collective inability to maintain continuous, verifiable understanding of what moves through orbit means that safety margins are eroding, and the rate at which uncertainty grows is beginning to exceed the rate at which knowledge is renewed. The ISS maneuvers to avoid known, tracked debris approximately once a year. The unknown debris is always there, and the unknown debris is getting more numerous.
Part 5. Normalization of Deviance Revisited. In 1996, sociologist Diane Vaughan published a book called The Challenger Launch Decision. It was about the Space Shuttle Challenger, which broke apart 73 seconds after launch on January 28, 1986, killing all 7 crew members, including schoolteacher Krista McAuliffe. The disaster was caused by the failure of an O-ring seal in the right solid rocket booster. Cold temperatures had stiffened the rubber, preventing it from sealing properly. Vaughan spent years studying the decision-making process that led to the launch, and what she found was not a story of negligence or incompetence. It was a story of something far more disturbing, a sophisticated technical organization that had gradually, through a series of individually reasonable decisions, drifted into a state where known risks were no longer perceived as risks at all. She called it the normalization of deviance. The concept works like this. An organization designs a system. On the first mission, something deviates from the specification, not catastrophically, just measurably. The deviation is noted. Engineers discuss it, management evaluates it, and because the mission succeeded, because no one died, the deviation is accepted as within operational limits. It becomes the new baseline. On the next mission, the same deviation occurs, and this time it is expected. Over time, what was originally a warning sign becomes background noise. What was originally a risk becomes an accepted feature of operation. And then, one day, the deviation that had always been there crosses a threshold that nobody saw coming. With Challenger, the deviation was O-ring erosion. NASA knew about it. Morton Thiokol engineers had documented O-ring erosion on flight after flight, had raised concerns, had written memos, had argued, some of them passionately, that the pattern was dangerous. The shuttles kept flying. 24 missions launched with known O-ring erosion before Challenger. Each survival reinforced the belief that the erosion was within acceptable limits. The risk was normalized. The deviance became the standard. On January 27, 1986, the night before the Challenger launch, Thiokol engineers spent hours in a teleconference with NASA arguing against the launch. The temperature at Kennedy Space Center was 36 degrees Fahrenheit, cold enough that icicles had formed on the launch pad overnight. The engineers had data showing the O-rings lost flexibility in cold weather. They had charts. They had test results. They had the voice of Roger Boisjoli, a senior engineer who would later testify that he felt physically ill watching the launch because he believed the O-rings would fail. NASA pushed back. The agency was under schedule pressure. There had already been multiple launch delays. Krista McAuliffe's presence on the crew had generated enormous public interest, and every delay was covered by the media. The conversation that night ended with Thiokol management overruling their own engineers. The launch was approved. Then, something happened in that conversation that Vaughn identified as the defining moment of the entire Challenger disaster. NASA did not ask Thiokol to prove that it was safe to fly. NASA asked Thiokol to prove that it was unsafe. The burden of proof had inverted. The default position had shifted from flying is permitted when we can prove safety to flying is prohibited only when we can prove danger. That inversion is how normalization of deviance crosses from institutional habit into active risk acceptance. It is the moment when the deviation stops being a concern and becomes an assumption. 73 seconds after launch, the O-ring failed. The shuttle was destroyed. 7 people died. 17 years later, on February 1, 2003, the Space Shuttle Columbia broke apart during re-entry over Texas and Louisiana. A piece of foam insulation from the external tank had struck the leading edge of Columbia's left wing during launch 16 days earlier. The foam strike damaged the thermal protection tiles on the wing. When Columbia re-entered at 18 times the speed of sound, superheated plasma entered through the breach and the orbiter was destroyed. 7 more people died. The foam strikes were not new. Engineers had identified foam shedding as an anomaly as early as the second shuttle flight. Over 113 missions, foam had impacted the orbiter's thermal protection system repeatedly. The strikes had been documented, analyzed, and, because the shuttles kept returning safely, gradually accepted as a known operational characteristic of the launch profile. The risk was normalized. The deviance became the standard. The Aerospace Safety Advisory Panel, which reports to NASA's administrator on safety issues, had warned about patterns of risk normalization at NASA in reports going back years. The Rogers Commission report after Challenger had warned about it. The Columbia Accident Investigation Board in 2003 warned about it again. By the time of Columbia, the board noted the institutional patterns that led to Challenger had been documented, studied, analyzed, and warned about for 17 years without being structurally corrected. Now bring that lens to the International Space Station. A leak was detected in the PRK module in 2019. It was small, it was manageable, it was monitored. The station continued to operate normally. The leak grew. In 2022, NASA began reporting it regularly to its safety panel. The station continued to operate normally. In February 2024, the leak rate jumped to 2.4 pounds per day. The program manager said it was not an impact right now on crew safety. The station continued to operate normally. In April 2024, the leak rate jumped again to 3.7 pounds per day. The risk was elevated to the highest score on NASA's scale. The interim measure of sealing the hatch when not in use was implemented. The station continued to operate normally. Two space agencies cannot agree on what is causing the leak, or on the definition of untenable, or on whether catastrophic failure is possible. The station continues to operate normally. I am not telling you that the ISS is about to catastrophically fail. I am not telling you that the decision to continue operations is wrong. What I am telling you is that the pattern, the sequence of observations, accommodations, normalizations, and continued operations in the face of unresolved risk is one that we have seen before. We have a name for it. We know where it leads when the underlying problem is not corrected. The O-rings survived 24 flights. The foam survived 113. The ISS leak has been growing for 5 years without a root cause determination, and the two agencies operating the station cannot agree on how dangerous it is. There is a second layer to this pattern that I want to address directly: the bilateral relationship within which all of this is happening. In February 2022, Russia invaded Ukraine. The international response included the severance of most collaborative relationships between Western nations and Russia: scientific cooperation, joint research programs, technology exchanges. NASA and Roscosmos have maintained their ISS partnership through this because the station's operations make unilateral withdrawal essentially impossible. The modules, the docking systems, the propulsion capabilities are architecturally interdependent. You cannot simply separate the American segment from the Russian segment and operate independently. But the relationship has changed. Russia has committed to the station through 2028, 2 years before the planned 2030 deorbit. And the November 2024 Advisory Committee hearing, Bob Cabana confirmed that Roscosmos has not given firm answers for its involvement after 2028, and likely won't until at least 2025 or 2026. And the station's deorbit plan, which I will come to in the next section, depends critically on Russian cooperation in the final 2 years of the program. Two agencies cannot agree on whether a 5-year-old leak is dangerous. One of those agencies has a geopolitically constrained relationship with the other, no binding commitment past 2028, and is operating within a war that has severed almost every other element of their international scientific collaboration. Diane Vaughan's concept of normalization of deviance assumes a single organization. What happens when the deviance is being normalized across two organizations that don't fully trust each other's data? That is a question that has no historical precedent. It is a question that is being answered in real time in the Russian segment of the International Space Station right now.
Part 6. The $150 billion problem of getting it down. The International Space Station was not designed to last forever. It was built for an operational lifespan that has already been extended multiple times, first from 2015 to 2020, then from 2020 to 2024, then from 2024 to 2030. The current plan calls for deorbit in 2030, driven into the South Pacific Ocean's spacecraft cemetery, the same remote area of the Pacific where Mir, the Salyut stations, and dozens of cargo ships have ended their operational lives. But deorbiting the ISS is not a simple operation. It is, in fact, one of the most technically and politically complex decommissioning operations ever attempted. Here is the scale of the problem. The ISS weighs approximately 420,000 kilograms. It is currently orbiting at roughly 420 kilometers altitude. To bring it down in a controlled manner, aimed at a specific, uninhabited stretch of the South Pacific rather than anywhere else on the planet, requires a series of precisely orchestrated orbital lowering burns across several years, followed by a final deorbit burn that commits the station to a specific re-entry trajectory. A controlled re-entry is essential. The ISS is too large to burn up completely in the atmosphere. Significant portions of the station's structure, particularly the dense, heat-resistant components, will survive re-entry and impact the Earth's surface. The spacecraft cemetery in the South Pacific is the target because it is the most remote stretch of ocean on the planet, maximally far from any populated coastline. Getting the debris to land there, and only there, requires precision that depends on both the deorbit vehicle and the thrusters of the station's own Russian modules. NASA contracted SpaceX in 2024 to develop the U.S. Deorbit Vehicle, or USDV, a specialized spacecraft derived from the Dragon capsule hardware, with additional propulsion systems that can provide the main thrust for the deorbit burns. That contract was awarded in June 2024. NASA's own Inspector General has noted that the average time from contract award to first operational flight for spacecraft of this type is approximately 8.5 years. The USDV needs to be ready by 2030. It has been under contract since mid-2024. That is 6 years, 2.5 shorter than average. The plan for the deorbit sequence depends not just on the USDV, but on the propulsion systems of the Russian segment. The Russian Zvezda and Zarya modules provide attitude control, keeping the station oriented correctly, while the USDV provides the main orbital lowering thrust. These two systems have to work together with precision across the entire multi-year deorbit process. Russia has committed to the ISS through 2028. The deorbit process begins in 2028. The critical final phases extend through 2030 and into early 2031. NASA's entire end-of-life strategy for the world's most expensive structure depends on full, active Russian cooperation for 2 years beyond the date to which Russia has formally committed. A U.S.-Russian joint commission met in February 2025 to discuss the deorbit sequence. Their joint plan calls for a 2.5-year process of slowly lowering the station's orbit, a process that cannot begin until 2028 and is contingent on the propellant tanks in the Russian Zvezda and Zarya modules being adequately fueled. Roscosmos officials have stated they expect to participate in the deorbit process, but there is no binding intergovernmental agreement that legally commits them to do so. And beyond the deorbit question, there is the budget question, which may be the most consequential of all. NASA's proposed FY 2026 budget, submitted by the Trump administration in May 2025, called for a 24% overall reduction from approximately $24.8 billion to $18.8 billion. Within that proposal, ISS funding was cut by $508 million. The proposal called for significantly reducing the number of crew and cargo flights to the station, shrinking the onboard crew size, and focusing the station's remaining research capacity exclusively on work directly relevant to Moon and Mars exploration. The language in the White House budget document was straightforward. The budget reduces the space station's crew size and onboard research, preparing for a safe decommissioning of the station by 2030 and replacement by commercial space stations. For context, as of FY24, NASA spent approximately $3 billion per year on ISS operations and crew and cargo transportation combined. The station costs about $4.1 billion per year when all associated costs are included, representing roughly 16% of NASA's total budget. Cutting $508 million from that means in practice fewer supply missions, fewer crew members on board, less maintenance, less science. In the final 4 years of the station's operational life, as it ages, as the leak continues, as the debris environment worsens, the budget for managing it would shrink. The Aerospace Safety Advisory Panel has raised explicit concerns about this dynamic. An uncontrolled deorbit, one that occurs because the USDV is not ready, or because Russian cooperation breaks down, or because the station's structural deterioration reaches a point that forces an emergency end of life, would result in a 420,000-kilogram structure falling from the sky without precision targeting. The debris field from an uncontrolled ISS re-entry would scatter across hundreds of kilometers of Earth's surface. The probability of populated areas being hit would be, according to the safety panel, substantially higher than a controlled deorbit. The agency's OIG report stated that the risk to the public would increase substantially if the USDV is not in place. And yet, the budget is being cut. The development timeline for the USDV is already compressed below average, and the political relationship with the country whose propulsion systems the deorbit plan depends on has never been more strained. Here is where I want to be careful and honest with you, because this is the section of the story that is easiest to tell badly. None of these problems individually are proof of impending catastrophe. The ISS has exceeded its original design life repeatedly, and its engineers have managed that aging with remarkable skill. The deorbit plan has significant challenges, but also experienced engineers working on them. The budget cuts are proposals, not enacted law. Congress will ultimately determine the actual appropriations. But the pattern of problems is real. The combination of a worsening structural leak whose root cause remains unknown, a health profile that includes the first medical evacuation in program history, a debris environment that is growing more dangerous every year, a deorbit plan that depends on Russian cooperation 2 years beyond their commitment, and a budget that is being cut as the station enters its most demanding final phase. That pattern is not something I invented. It is in the Inspector General reports. It is in the Aerospace Safety Advisory Panel assessments. It is in the documented record of what is actually happening.
Let me bring you back to the numbers I gave you at the beginning. 3.7 pounds of atmosphere per day, classified as 5 by 5, the highest possible risk score. A root cause that 5 years of investigation has not identified. 2 agencies that cannot agree on whether catastrophic failure is possible. 70% of long-duration residents developing a syndrome that can permanently alter their vision. A first medical evacuation in 25 years on an astronaut who may have experienced a transient neurological event that he described as likely a space-related thing. 130 million pieces of debris, the smallest of which cannot be tracked, all of them traveling at 10 times the speed of a bullet, surrounding the station on every orbit. A deorbit plan whose most critical phases depend on a country that has committed to 2028 in a program that ends in 2030, executed through a partnership strained by a war that has severed most other elements of their collaborative relationship. A budget that is proposed to shrink by more than $500 million as the station enters the most technically demanding phase of its existence. Individually, you can construct a reassuring answer to any one of these problems. The leak is being monitored. The medical protocols are robust. The debris environment is managed with avoidance maneuvers and shielding. Russia has stated its intention to cooperate with the deorbit. The budget proposal is not a final appropriation. But here is what I keep returning to, the thing that I think the data is actually saying when you hold all of it at once. The International Space Station is 25 years old. It is older than it was designed to be. It is losing air through cracks that no one can fully explain. The people living inside it are developing biological changes that we do not fully understand on timescales that may not become fully visible for years or decades. The environment surrounding it is more dangerous today than it was yesterday, and will be more dangerous tomorrow than it is today. The plan for its retirement depends on a geopolitical relationship that is under severe strain, executed on a compressed timeline with a budget that is being reduced rather than increased. And the press coverage of the International Space Station is almost universally a story of wonder. Astronauts doing science, beautiful photographs from the cupola, milestones and anniversary celebrations, and the occasional inspiring spacewalk. All of it real, all of it genuine, none of it the whole story. Diane Vaughan identified the normalization of deviance in 1996. The Aerospace Safety Advisory Panel warned NASA about institutional risk patterns after Challenger in 1986. The Columbia Accident Investigation Board repeated those warnings in 2003. The Inspector General's reports have been documenting the ISS's structural risks since 2021. The warning signs are always in the record. The question that is always the same is whether anyone is reading it. The Challenger engineers warned about the O-rings for years before the disaster. 24 flights went safely with known O-ring erosion. The foam was documented on 113 Columbia missions before the final one. The data was always there. The question was always whether the institutions responsible for acting on it were willing to let it override the momentum to continue flying. I do not know what happens to the International Space Station between now and 2030. Nobody does. The record of human engineering is one of resilience and ingenuity under pressure, and the people working on these problems are extraordinary. It is entirely possible that the leak is managed to the end of the station's operational life, that the deorbit goes precisely as planned, that the commercial stations that are supposed to replace the ISS are ready before the gap opens, that the budget fights resolve in NASA's favor. It is possible, and I genuinely hope it is the outcome. But the data, the actual data, not the press release, suggests that the gap between where we are and where we need to be in 2030 is narrowing on multiple fronts simultaneously in a program operating under budget pressure, against a geopolitical backdrop that has no clear resolution, inside an institutional culture that twice in living memory has been documented normalizing deviations until they became disasters. The ISS is not a failure. The science that has been done aboard it has genuinely advanced human knowledge. The 25 years of continuous human presence in orbit is one of the most remarkable achievements in the history of exploration. The 270 people who have lived there and looked out the cupola and seen the Earth whole from 400 kilometers up have experienced something that changes how you see the species you belong to. And somewhere in the Russian segment right now, a module is losing air at a rate that neither of the agencies operating the station can fully explain, through cracks they can only locate using floating tea leaves at the highest risk classification on NASA's scale. That is the state of the most expensive structure humanity has ever built. The question of whether we're managing it with the honesty and rigor it deserves, whether the data is being allowed to override the momentum, whether the warnings in the OIG reports and the safety panel assessments are being taken as seriously as they should be, whether we're being honest with ourselves and with the public about the gap between the celebration and the reality, is a question that none of the press conferences will answer. It is a question that gets answered slowly, in rooms that nobody films, in decisions made by engineers and managers and budget officials whose names most people will never know. It gets answered in whether the hatch to the PRK module has to be permanently sealed. It gets answered in the SAN's data collected from the crew members returning in 2026 and 2027 and 2028. It gets answered in whether the USDV is certified on time or not. It gets answered in whether Russia is at the table in 2029 when the orbital lowering sequence begins. The ISS will come down. That is not in question. The question is whether it comes down on our terms. The data, as of today, leaves that question genuinely open. And I think that, strange as it might sound, might be the most important thing the International Space Station's final years are confirming about our future in space. Not that we cannot do extraordinary things, but that the gap between the extraordinary things we do and the ordinary honesty with which we talk about their risks remains wider than the view from the cupola.